Welcome to the Chapter 6 Part 2 notes video. We are going to be looking at some operations that we can use on vectors. So we're applying some of the things that we learned in the last section and doing some new things with them. We're specifically going to look at the dot product, which is a new type of multiplication where we can now multiply two vectors. Remember, before we could only multiply a vector by a number. That was called scalar multiplication. And then we're also going to look at using the dot product to find the angle between two vectors. And this time we're not using the positive x-axis as our second vector. So we've found the angle between the x-axis and any vector. Now we're looking at two vectors that are not on the positive x-axis necessarily. And then finally, projecting one vector onto another, similar to how a movie projector would project onto a screen, we're doing one vector projecting onto another. So if we think about the vector as having a shadow that would land on another vector. Why is this important? Vectors are used a lot in math and science. For example, in physics, it's used a lot of times, vectors are used to represent effects of forces on an object. So you'll see a lot of vectors in physics. So the dot product. Dot product is a new type of multiplication. It's also sometimes called the inner product. And notice this time we are multiplying two vectors. So when I'm multiplying u times v, I could also write that as multiplying u1 comma u2 vector times the vector v1, v2. And the way that this works out is we're really multiplying the x components, and then we multiply the y components and we add them together. So we can think about this as x1 and x2 plus y1 and y2. Notice this will give us a scalar. That's going to give us just a number. Our answer for a dot product is going to be just a number. Whereas when we had before the scalar multiplication, we had a number times a vector, and our answer was a vector, right? So when we used scalar multiplication, we ended up with a vector, and now we have a dot product where we multiply two vectors and we end up with just a number, which is called a scalar. Okay, some properties for the dot product. We have the commutative property, meaning u times v is the same as v times u. We can also use now dot product to find the magnitude. So we can say a dot product of a vector with itself, u times u, is equal to the magnitude squared. This is magnitude. We can say any vector times the zero vector will give us a scalar of 0. So if we think about that, that would mean 0, 0 times u1, u2, which would be 0 times u1 plus 0 times u2, which is in fact 0. And then we can say, kind of like the distributive property for multiplication, if we add two vectors and multiply them by another vector, that's the same as adding the product of the vector times each of the vectors separately. This is like distributive. And you still end up with a scalar. Still a scalar result. So the answer for a dot product is still just going to be a number. Same thing if we add them and then multiply versus multiplying and then adding. We've already seen that as the commutative property in number 1. And then finally here in number 5, this is a scalar multiplication. Notice the C is not bold. So if I multiply a number times a vector and then I multiply the two vectors, that's the same as if I multiply the number times the other vector. So again, the commutative property works for scalars and vectors mixed together. So this is scalar, C, and vectors, U and V. Let me adjust so that I can write scalar better. There we go. So commutative property, we saw it 3 times. We know we can use the commutative property for vectors now, as well as numbers or scalars. Okay, let's look at an example. we want to find the dot product. When I do the dot product, I either usually line them up vertically or I actually draw these little lines. So I know that I'm multiplying the x values, 4 times -1, and then I'm adding that to our y values, which is 3 times -2. -4 plus -6 gives me -10. It's not a vector, just a number. If I line them up vertically, 4, 3 times -1, -2 dot product, then I can say that's -4 plus -6 equals -10. So you can do it either way if you have a preference of which one visually makes more sense to you. Okay, I said we could now use dot product to find the angle between two vectors, so we have a formula for that. To find an angle between two vectors, we can use the cosine function. Cosine equals the dot product of two vectors divided by their magnitudes. So this is going to be a dot product is a scalar divided by the magnitudes, which are both scalars. So this is cosine theta equals some number, right? And that's what we would expect for cosine. We wouldn't get a vector from a cosine value. So we can see that this will work out in terms of taking cosine of an angle should give me a length. And then if we solve that for theta, we end up with cosine inverse of the dot product divided by the magnitudes. Let's look at an example. We want to find the angle between these two vectors. The first thing I'm going to do is draw a picture. So vector u, -2, 3, means I go from the origin left 2 up 3, just like plotting a point on a graph. Vector v is -4, 1. Find the angle between the vectors. So I'm looking at this angle between the two vectors. I know that it's going to be definitely less than 180 degrees, right? Because they're in adjacent quadrants. But it looks to me like that's probably going to be a little bit less than 90 degrees even, because from my diagram, I can see it looks like an acute angle. So that's going in with the expectation, I'll know whether my answer makes sense. So our formula here, I'm going to write the original cosine of theta equals u dot v divided by the magnitude of u times the magnitude of v. That means I'm going to need the magnitudes. Theta equals cosine inverse of, and I'm going to do some of the calculations off to the side. So we have -2, 3 dot product with -4, -1. That gives me +8 plus -3. I'm just multiplying down and then adding them together. So that's 5 divided by, that was u dot v. Now I need the magnitude of u. To find the magnitude, we take the square root of each component squared. So that's the square root of 4 plus 9, which is the square root of 13. And then the magnitude of v. So that's the square root of each component squared and add them together. So that's 16 plus 1 is the square root of 17. That's, I'm going to put directly into my calculator. Make sure you're using cosine inverse. So that's second cosine, 5 divided by parentheses, square root of 13 times the square root of 17. If you're worried about your parentheses in the denominator, we know that the property of the square roots we can multiply. So cosine inverse of 5 divided by, I can also write this as the square root of 13 times 17. Then I don't have to worry as much about parentheses because I have just a single factor in the numerator and the denominator. Making sure I'm in degree mode, if I'm going to give my answer in degrees, I can say that theta equals 70.346 degrees. And if I want the answer in radians, then I would go and make sure that my mode is in radians. Doing the exact same calculation, I can say that that is 1.228 radians. I didn't specify, so either answer is correct for this problem. Make sure when you're reading on Math Excel, they have that blue writing underneath the answer box that will specify what units to use if it's not already specified in the problem. So that's the angle between. We were expecting it to be acute, but just a little bit acute, right? So not like a 10-degree angle, but 70 degrees is acute, so it matches what I was expecting. Always good to do a logic check at the end. Okay, so when we're finding angles between vectors, sometimes we end up with a dot product of 0, and that gives us actually a very special angle between vectors. So if I ever have perpendicular vectors that create a 90-degree angle, and that could be any two vectors that create a 90-degree angle. They don't have to be quadrantal angles. They don't have to be on an axis. The word that we can use to describe this relationship is orthogonal. So orthogonal means that two vectors are perpendicular, but it also means I could be trying to find the angle between a vector and the 0 vector. Now remember, the 0 vector has no length. It has a magnitude of 0, and therefore it doesn't have a direction either. And that means any vector times the 0 vector, or dot product with the 0 vector, will give me a dot product of 0. Okay, so we call both of these cases, perpendicular and the case with the 0 vector, together are called orthogonal. So if I know that the dot product is 0, that doesn't necessarily mean that I know that the two vectors are perpendicular, because one of the vectors could be the 0 vector, which can't be perpendicular because it doesn't have a direction. So we have this new word that kind of encompasses perpendicular, but also our new case where we have a 0 vector. And we can always find that out by finding the dot product of the two vectors. So this is a special case of the angle between two vectors. If we think about the dot product is 0, 0 divided by any magnitude is going to be 0. And if I have cosine of theta equals 0, then theta must equal, if cosine of theta is 0, that means my x on the unit circle is 0. So that's 90 or 270 degrees, either of which gives me a perpendicular angle. Okay, so that is orthogonal, a special case of dot product. The last thing I want to cover in this video is called projections. And we're going to do the calculations together because this one can get a little bit tricky. What I want to point out first from the formula is that it's very, very similar to our angle formula, right? We start with a dot product in the numerator and magnitudes in the denominator, but there's a big difference here. And that is that in my denominator, I have the magnitude of v times the magnitude of v, or the magnitude of v squared. And then I'm multiplying that, which will be a scalar, by a vector. And if I multiply a number to a vector, my answer is going to be a vector. Okay. We also know from our definition, or properties rather, of dot product that v dot v was the magnitude of v squared. So another way that I can write, I can say that this is u dot v divided by v dot v times v. So notice it's all v's except for our very first u. And what that means is that if I have two vectors, I'm going to do one in a different color. What I'm looking for a projection is, let's call the red one vector v. What a projection means is I take u and I draw a line that's perpendicular to the head of u towards v. So I'm looking for that perpendicular, kind of like drawing an altitude of a triangle. And the resulting vector from their point in common to that perpendicular point is the projection of u onto v. So it's part of v. It's a piece of vector v, but it comes from, like the shadow of vector u. So that's what that means. Okay, everything is part of vector v. That's why we multiply it by vector v at the end. This is going to be part of vector v. Okay, so that's what a projection means. We're going to do examples together in class.